Okay, hello everyone in a new video. So we have reached part 3 of chapter 7, which is the chapter of Newton's second law for grade 11 students. Okay, so in this part we are going to solve some exercises, but before we start, let me make the following note. So note number 1, as we have said previously, that A is equal to 0 may be due to equilibrium, or even V is equal to a constant. Recall that V is a vector quantity, it must be constant in both direction and magnitude. And as we have said previously, that the variation in the direction in v causes the normal acceleration. Now the second note that I want to pose is given by sum of forces is equal to ma gives the birth of two equations so, and in this case the number of unknowns must be less or equal to 2. So sum of forces is equal to ma gives the birth of two equations, and in this case the number of unknowns must be less or equal to 2. And the type of equations here, I didn't specify the type of equations. The type of equations depends on the problem itself, okay? So now let's start by exercise number 3. They are telling me a sphere of mass m. So the moment we have the mass, then it will be subjected to the weight. Is suspended from a light string, so we don't know the mass. So here, because we have a mass, we have a weight which is vertically downward like this. And because if we have a string, then we will have a tension along the string, which is like this. The sphere is pulled by horizontal force F of magnitude F is equal to 2 newtons. The sphere maintains equilibrium where it makes an angle alpha is equal to 40 degrees with respect to the vertical. Take G is equal to 10 meters per second square. Now in number 1, they are telling me name and represent the forces acting on the sphere. So notice that here, as it seems from part 2, we are interested in applying, let me say here, Newton's second law. Name and represent the forces acting on the sphere. So as it seems that you are interested in applying a Newton's second law, so let me write here on the scratch the different steps regarding this law. Then step number 1 is to list the forces. Step number 2, choose a reference system. Step number 3 is to project the forces. And step number 4 is to use equation sum of forces is equal to ma and the project. Okay, now They are telling me name and represent the forces acting on the sphere. So because it has a weight, it has a mass, then it has a weight, W. Now the other force is given by the horizontal force F. And because we have a string, then we have a tension T. Let's represent these forces. So we are done with step number 1. Let's represent these forces in a reference system. Let's choose this is the x-axis, this is the y-axis, this is the support here. The string is connected to the support like this. This is the vertical. So here we have alpha is equal to 45 degrees. This is the tension T. This is the horizontal force F. And this is the weight. So this is alpha also. So notice that if this is 45 degrees, then pi by 2 minus 45, this is equal to 90 degrees. So 90 minus 45, it will be also equal to 45 degrees. So this is given by also 45 degrees. This is the positive x-axis, this is the positive y-axis, this is I, and this is J. Okay, so this is the representation of the forces. Now in number 2, they are telling me by determine applying Newton's second law. For part A, we are interested in the tension. So now we are done with step number 1, step number 2. Now in step number 3, we need to determine the projection of the forces. Let's start by the force T. So as for the x component, notice that it's pointing in the negative direction of the x-axis, so it's minus T cosine 45, which is equal to minus radical 2 over 2 T, because the value of cosine 45 is radical 2 divided by 2. Now as for Ty, it's pointing in the positive direction of the y-axis, so it's plus T cosine 45, because the angle between the T and the y-axis is given by 45. So this is equal to radical 2 by 2 T. Now as for the force W, Wx is simply 0 because W is completely lying on the y-axis, so it's minus W. And as for the force force F, it's completely lying on the x-axis, so of x it's a plus F and Fy is 0. Now we are ready to use Newton's second law. So here, because it is at equilibrium, then instead of applying Newton's second law, we can say at equilibrium, or we can say apply Newton's second law, it's the same. So let's say at equilibrium. This is indeed a Newton's second law, which is given by sum of forces is equal to 0. Now on the left hand side, we write the different forces acting on this sphere, which is given by the tension, the weight, and the horizontal force. And on the other side of this equation, we write the zero vector corresponding for the condition of equilibrium. Now in part A, we are interested in determining the tension. So notice that the tension appears in the x component. So let's use the x component, say for example. So T appears in the x component. Let's use the x component. So let's say projection along the x-axis. Then in this case, simply we drop down the vectors and each vector quantity will carry the label x. So we drop down the vectors and each vector quantity will carry the label x. Now Tx is given by minus radical 2 by 2t. Wx is given by 0. Plus Fx, the capital F given by this, is equal to 0. Now let's check if you know the value of F. So yes, F is given by 2 newtons. So in this case, what's the type of this equation? This is a linear equation and one unknown. The unknown is t. We put t on one side and all the other numbers on the other side. So t is given by 2 divided by square root 2 over 2. So this is given by 4 divided by radical 2, which is equal to 2 radical 2. Since F is expressed in newtons, then the value of t will be expressed in newtons because all quantities in physics must carry a unit. Okay, let me check on the calculator. So one second. Sorry, this is simply given by radical 2. And t is given by radical 2. Now suppose that you have chosen the y component in order to solve for t. Notice that as for the y component, let's count the number of unknowns. We have t and we have w. Okay, so in that case you will also need the x component in order to solve for t. Now in part B they are telling me to determine the mass of the sphere, which means to determine the weight. Now we have already made use of the x component. Let's make use of the y component. So we are on part B. Let's perform the projection along the y-axis. So in this case we drop down the vectors and each vector quantity will carry the label y. Ty is given by radical 2 over 2t. Wy is given by minus w and Fy is 0. So what's the type of this equation? This is a linear equation and one unknown. The unknown is w. We have already determined the value of t, which is given by radical 2. So w is given by radical 2 over 2 multiplied by radical 2, which is equal to 1 in newtons. So the magnitude of w is given by 1 newtons, but recall that we are interested in determining the mass of the sphere and not the weight. So weight, mass, and g are related via the following formula. Weight is equal to m multiplied by g. So simply m is the ratio of w over g. So 1 divided by 10, then the mass of the ball is given by 0.1 kilograms. Now let's move to the next exercise, exercise number 4. They are telling me a floodlight of mass m is suspended from 2 cables as shown in the adjacent figure. The tension T1 on the right has a magnitude T1 is equal to 140 newtons. Now before I solve this exercise, also let me make the following note. Okay, I will make the note during the exercise. Now the tension T1, the tension force T1 on the right has a magnitude T1 is equal to 140 newtons. Assume that the 3 cables are light and inextensible. So by inextensible it means that the cable or the string can transmit tension at its free ends. Okay, take G is equal to 10 meters per second square, which is equal to 10 Newton per kilogram. Now in number 1 they are telling me represent the external forces exerted on the node A. So here let's always keep an eye on the different steps that we usually follow in order to apply Newton's second law. And the steps are given by step number 1, list the forces. Step number 2 is given by choose a reference system. Step number 3 is to project the forces. Step number 4 is to use this equation sum of forces is equal to MA and to project. Okay, so always whenever you are interested in solving a vectorial equation, it's better to project it. Now in number 1 we need to represent the forces acting on the node A. Now here the note that I want the note that I wanted to make is that in a problem several bodies may be included in the system. So here the system is made up of two bodies, the body A and the body S. Okay, and here we need to be careful. They are asking me about the forces exerted on the node A. So we ignore the body S, we only take the body A and we represent the forces that are only acting at the body A. So only consider the body A. Okay, now what are the forces acting on the body A? Here, okay, suppose that the mass of A is 0, so the point A has no mass, so it will be not subjected to the weight. Okay, so what are the forces acting on the node A? We have the tension T1, we have the tension T2 along the string, and we have tension T3 along the string. So what are the forces? We have the force, okay, we will represent them, but first let me list the forces. We have the force T1, tension T1. We have the tension T2 and tension T3. No weight is acting on A since its mass is negligible. Okay, so for this reason I didn't mention the weight acting on the point A. Okay, so these are the forces that act at the point A, and I repeat, whenever we are considering A, we ignore other bodies, we just consider the point A. So what are the forces acting on A? We have T1, T2 and T3. So these are the external forces acting on the node A. Now in number 2 they are telling me determine T2, the magnitude of the tension force T2 in the left cable. So since we are interested in T2 and T2 is related to node A, so we need to apply the equilibrium of the condition of equilibrium, and it includes a vectorial equation. In order to solve this equation we need to consider several steps. We have already done with the step number 1, which is the list the forces. Now let's just choose a reference system. So suppose that this is the x-axis, and this is the y-axis. This is the positive direction of the x-axis, and this is the positive direction of the y-axis. This is I, and this is J. Suppose that this is the support like this. This is the first cable or string. This is the second cable here. And the reference system is chosen at the point A. Here we have the tension T1. Here we have the tension T2 in the cable. Okay, so if this is 40, then this is 40, which which is pi, it's the same, and this angle is pi by 2 minus 40, or 90 degrees minus 40, so this is 50. If this is 60, this is 30, and eventually this is, sorry, this is 60, and eventually this is 30. Okay, now it's left to represent the force T3. So always the tension acts away from the body, so away from the body it's vertically downward. Notice that always the tensions act away from the body, so T1 is acting away from the body A, T2 acting away from the body A, and T3 acting away from the body A. Now we are done with the step number 2, so now let's project the forces. Let's start by the force T1. So the force T1, let's start by its x component. Notice that T1 is positing in the positive direction of the x-axis, so it's plus T1 multiplied by cosine 60, which is equal to half T1. T1y is equal to plus T1 cosine 30, because 30 represents the angle between T1 and the y-axis, so it's radical 3 over 2 T1. Now as for the force T2, so T2x, notice that T2 is pointing in the negative direction of the x-axis, so it's minus T2 cosine 45, which is equal to minus radical 2 over 2 T2. T2y, pointing in the positive direction of the y-axis, so it's plus T2 cosine 45, which is equal to radical 2 over 2 T2. As for the force T3, T3 is completely lying on the y-axis, so T3x is 0 and T3y is equal to minus T3. Now after we have determined the component of the forces, we are ready to deal with the equilibrium condition. Why equilibrium? Because simply it's not moving, or we can say apply Newton's second law. So let's say at equilibrium, so how do you apply this condition? Always on the left we write the sum of forces acting on the node A. So here let me write between brackets for the point A. So on the left hand side of this equation we have T1 plus T2 plus T3, and on the other hand side of this equation we write the zero vector corresponding for the condition of equilibrium. We are interested in determining the magnitude T2, but notice that T2 in this case appear in x and in y. So let's start by the projecting along the x-axis. Probably, okay, no, projecting along the x-axis will solve the problem, because the other unknown, which is T3, doesn't appear along the x component. So let's say projection along the x-axis. Then in this case, simply we'll drop down all the vector quantities, and each vector quantity will carry the label x. Then T1x plus T2x plus T3x is equal to 0. Now T1x is given by half T1, T2x is given by minus radical 2 over 2 T2, and T3x eventually is given by 0, which is equal to 0. Now we have the value of T1, which is given by 140 newtons. So in this case, what's the type of this equation? Linear equation of one unknown. The unknown is T2. How do we solve it? We put T2 on one side and other numbers on the other side. So T2 is given by half T1 divided by radical 2 over 2. So T1 divided by radical 2, which is equal to 140 divided by radical 2. Plugging this on the calculator, then the value of T2 is given by 98 or let's say 99 newtons. So the value of T2 is given by 99 newtons. Now in number 3 they are telling me calculate T3, the magnitude of the tension force T3 and the vertical cable. So notice that also T3 appears as a force acting on the body A, which means that we can make use of the condition of equilibrium at the point A in order to determine T3. So because we have made use of the projection along the x-axis, now let's project along the y-axis in part 3. Now simply we drop down the vectors and each vector quantity will carry the label y. Now T1y, which is equal to minus radical 3 over 2 T1. Let me make sure of that. Let me check the angles. Yes. Okay. Now T2y is given by radical 2 over 2t. And T3y is given by minus T3. Knowing that we are interested in determining the value of T3. So what's the type of this equation? This is a linear equation on one unknown because we know the values of T1 and T2. So T3 is equal to radical 2 over 2 T2 minus radical 3 over 2 T1, radical 2 over 2 T2, and the value of T2 is given by 99, minus radical 3 over 2 T1, and the value of T1 is given by 140. So plugging this on the calculator, probably there's something wrong. There's something wrong here. This is plus, okay. So notice that this is plus here. There is no minus sign. Now plugging this on the calculator, so this is equal to 191.25 newtons. Then the magnitude T3 is equal to 191.25 newtons. So this is it for number 3. Now in part 4 they are telling me deduce the mass of the floodlight. Now in part 4 they are telling me deduce, and by deduce it means that we need to use the previous part. In the previous part we have determined the magnitude T3 along the tension. So how come we need to deduce the mass of the floodlight? The mass of the floodlight, which means that we are interested in determining the weight of the floodlight. So here we need to apply Newton's second law or the condition of equilibrium, but not for the point A, for the other body that consists in the problem, which is the body S. So in this case, let's list the forces that act on the body S. So on the body S, we have the weight W, and we have, so if you consider the body S to be this body, so we have the weight which is acting vertically downward like this, and we have tension T3 which is acting vertically upward like this. And notice that in this case the direction of the tangent T3 is vertically upward and not vertically downward. So let's say that this is not T, let's say this is T prime 3, because already we gave a name for this force, which is C3. So in this case T prime 3 will be acting away from the body, as because always the tension acts away from the body. And we have the tension. Okay, so let's say T3 also, although this T3 vector is different than the first. Okay, so we are done with step number 1. Now let's choose a reference system. So suppose this is the x-axis and this is the y-axis. So this is the positive direction of the x-axis, this is the positive direction of the y-axis, this is I, and this is J. So suppose here the center of gravity of the solid S, although the weight is acting vertically downward like this, and the tension T3 is acting vertically upward like this, but these are free vectors, we can change their location. So T3 is acting vertically upward like this, and the weight is acting vertically downward like this. Now we are done with step number 2. Now step number 3 is to project the forces. So as for the force W, we have that Wx is equal to 0, and T3 and Wy is equal to minus W. As for the force T3, we have that T3x is equal to 0 and T3y is equal to minus T3. So we are done with step number 3, which is projection of the forces. Now we are ready to apply Newton's second law, or say at equilibrium. So now let's say at equilibrium, and here we are applying the condition of equilibrium for the body S. Notice that here I have set for the point A. So here let's say for the body S, then we will say that sum of forces is equal to 0 vector. In this case, what are the forces that are acting on the solid S? We have the weight plus tension T3, which is equal to 0 vector. Now after doing so, we need to project along the x-axis and along the y-axis. So notice that here no need to project along the x-axis because neither force lies on the x-axis. So we are only interested in projecting along the y-axis. So in this case, we drop down the vector quantities, and each vector quantity will carry the label y. So wy plus t3y is equal to 0. So 0y is exactly 0. Now the value of wy is minus w. Now here t3y is plus t3, because t3 is pointing in the positive direction of the y-axis. So plus t3, which is equal to 0. Here let me say that this is t prime 3, and this is t prime 3. To change them again, this is t prime 3, this is t prime 3x, t prime 3x, t prime 3. Okay, t prime 3 and t prime 3, t prime 3. So now w is equal to t prime 3, but t3 is equal to t prime 3, and the reason is given by an extensible string. So in this case, the value of W is simply given by 191.25 newtons. But notice that they are asking me, so if we refer back to this is T prime 3 and this is T3. They are equal in magnitude because the string, as they have mentioned, it's light and inextensible. But moreover, they are asking me about the mass, and the mass is determined from the weight because M is equal to W divided by G. So this is simply given by 19.125 kilograms. So the mass is given by 19.125 kilograms. Okay, and now here let me make the following note. This can be done using another method. So instead of solving and projecting, we can say that because at equilibrium we have that W plus T3 vector is equal to 0 vector. Here for sure we have sum of forces is equal to 0. Now in this case we have the W. Now dragging T3 prime vector to the right hand side, it will be minus T3 prime. So because this equation only consists of two vectors, no need to project, and we can directly say in magnitude that W is equal to T prime 3 without using what? Vector projections. So in this case, let me make the following note. So this is note number 3 for this video. Whenever a vectorial equation consists of two vectors, no need to project, and it can be solved directly. So suppose that if A plus B is equal to 0 vector, so no need to solve it because if we drag B to the right hand side, it will be A is equal to minus B. This equation means three things: that A and B have the same line of action, opposite direction, and same magnitude. If the vector equation includes more than three vectors includes three vectors or more, then we will refer to the projection method. Now note number 4. Suppose here we have the following bodies. So here we have a solid A, a solid B connected to each other via a string, an extensible string, and this is a support. If the system includes several bodies, sometimes it is required to apply sum of forces is equal to MA for several bodies. So we can apply for A, and we can apply sum of forces is equal to MA also for B. In which now, if you consider this equation will represent the mass of A, the acceleration of A, and the forces that are acting on A, and they are given by the weight, and this tension, and this tension. Okay, if you consider the sum of forces is equal to MA for B, we will consider the mass of B, the acceleration of B, and the sum of forces that are acting on B, and they are given by this tension only and this weight. Okay, so that's it for me in this video, guys. See you soon and anyone.